Today we are counting subsets, and so to do that I need to define binomial coefficients. Here are two different notations. This C and K is sometimes used, but this notation is read in choose K, and this is primarily the notation I will use and is also used in our text. Okay, well, what is this? By definition, in choose K is the number of K element subsets of an n element set. So in particular, n and k should be non-negative integers, and for this to be defined, k should be less than or equal to n, for example. Well, another way to think about this, and this is really where the n choose k comes from, you can also think about this as a number of ways to choose k elements from n. There is no order here. There is no order to a subset. And if you just choose k things, okay, there's no order there. It's just a choice. You can think about the k elements as just sitting in your hand, but they are not lined up in an order that was lists, like we talked about last time. Well, let's just do an example really to think about this binomial coefficient and to compare to this p and k, which we did discuss last time. And that is, let's consider the set 1, 2, and 3. And so we have these two things. We have 3, choose 2 versus p, 3, 2. And this is all two-element subsets. Well, we see it above. But this other thing, p3, 2, this was lists of length 2, or the number of lists of length 2 from this set 1, 2, and 3. Okay? No repetition, and this was an important part. And I also referred to this last time as with the 2 here, it would be a 2 permutation. It's orderings. But in a list, order is something, right? If you switch the order, it's a new list. And a subset, which is what n choose k counts, we know a subset, if you switch the order of elements between the brackets, it does not change the subset at all. Okay, so these two won't be the same number. For instance, well, we had a formula here which came from multiplication principle. This was 3 factorial over, let's see, it would be 3 minus 2 factorial, which is just 3 factorial over 1 factorial. This is 3 times 2. So we should have 6 lists of length 2 coming from this set with no repetition, and we can write them all out. And maybe on this side, we will write out all 2-element subsets to sort of compare these two numbers. Well, I have the subset containing 1 and 2. I have the subset containing 1 and 3. I have the subset containing 2 and 3. And these are all 2-element subsets of this larger set. We see, just from this calculation, right, we see that this is 1, 2, 3. This 3, choose 2, is 3. Well, I should have 6 over here, lists of length 2, and maybe I will fill this in the way that I would actually count them, which is I have 3 possible choices for the first entry. I could either have 1 or 2 or 3, and then for each choice of first entry, I have 2 choices of second entry if I am sticking to this no repetition. Here I can have a 2 or a 3. Here I can have a 3 or a 1. And here I can have a 1 or a 2. And you see, this is all possible lists of length 2 with no repetition. This number is definitely bigger, as it should be, because, for instance, 1, 2 and 2, 1. They're two different lists, but they both correspond to the same underlying set. And 1, 3, 3, 1, two different lists. Again, they correspond to the same underlying set. And the same thing for the last two, 2, 3 and 3, 2. They correspond to this underlying set. Now, at the very end of this lesson, we will get a formula for n choose k generally, but I don't want to start that way because I really want to think about this n choose k as definition, counting the number of k element subsets of an n element set. So we see one example that 3 choose 2 is 3 by listing them. But let's calculate a few other binomial coefficients, just thinking about subsets. Well, here, what would n choose 0 and n choose n be? Okay, this is how many 0 element subsets are there from an n element set. This is 1. The only 0 element subset of an n element set is the empty set. So there's only one. It's the empty set. Now similarly, what's n choose n? This would be the number of n element subsets from n element set. Okay, this is just 1. Okay, I'll say if A has n elements, then A itself is the only n element subset. So these two we can count. What's another one we can count? We can count and choose 1. This counts all 1 element subsets of an n element set. Well, this is just the singletons, and this is just the number of elements because let's suppose A is A1, A2, out 2, AN. Then, how do we get all the 1 element subsets? Like I said, this is the singletons. So this would be A1, A2, there's one with A3, and then out to AN. We see there are n of them. So n choose 1 is n. We calculated these 3 binomial coefficients without a formula, just by thinking about the definition, the number of k element subsets of an n element set. Now, there is another relationship that I would like to discuss, and then perhaps we will talk about why these are called binomial coefficients. Okay, well, it's the following, that n choose k equals n choose n minus k. This holds, okay? Now, why is this true? This is what I would like to discuss next. Well, this is kind of a cool thing to think about. Let's suppose I have a universe U with cardinality n, and then this side we know counts k element subsets of U, and this side counts n minus k element subsets of U. Well, also, why is this the same? Okay, let's take A with cardinality equal to k. This corresponds to, well, what subset has cardinality n minus k? It would just be a complement. This corresponds to a complement. And a complement has cardinality n minus k. And every choice of subset of size k, well, is really equivalent to choosing a subset of n minus k, which is its complement. Now, how can we think about this in an example? I did an example last time. We had a class of 30, and I was going to line up some at the board. There was order there. But let's go back and think about our class of 30. So we have a class of 30, and I want to take, I will take 6 students to pizza. There's no order to this. It's just I have a group of students, 6 of you, and we're going to pizza. Okay, well, I could specify the 6 And this is one choice. There would be 32, 6 number of ways to do this. But this is the same as, I'll say to take. I could also specify this 6 to take by giving the 24 that can't come. So if I said, okay, I'm going to take 6 of you to pizza, here's a list of 24 that cannot come. You would know exactly the 6 that can. This is the same as specifying the 24 who do not go. And this is this relationship. This is why n choose k is equal to n choose n minus k. Okay. Now, the next question that I want to address is why in the world are these called binomial coefficients? Well, generally, a binomial it's a sum of two terms. And these are called binomial coefficients because they appear as coefficients when you expand a power of a binomial. And this is what's called the binomial theorem. So let me state this. I will state this for natural numbers. If you have x plus y to the n, okay, so here's a power of a binomial, that this is a sum. Let's say k goes from 0 to n of n choose k, and then we have x to the k, y to the n minus k. So the powers here, the powers of x and y, they all add to n, and in each term, just as a comment. And this is the binomial theorem. Let's look at an example where we expand this fully. We'll take x plus y cubed, and I can write out all the terms in this case. This would be 3 choose 0, x to the 0, y cubed, plus 3 choose 1, x to the 1, y squared, plus 3 choose 2, x squared, y to the 1, and then finally we have 3 choose 3, x cubed, y to the 0. Okay? Now these coefficients, we know what they are. This number, n choose 0, is always 1. N choose 1 is n. This we calculated. This is our first example. We listed all 2 element subsets of a 3 element set. This is 3, or if we hadn't have done that, we could have used this relationship that n choose k is equal to n choose n minus k. And here with k is 1, that would say 3 choose 1 is equal to 3 choose 2. Okay, so we see that 3 choose 2 is 3, 2 different ways. And then finally here, this one is 1. The binomial theorem is something you can use. We will use it in math reasoning. In fact, I will do a proof with the binomial theorem momentarily, but you can also use it in other classes because think about how many math classes you have to expand things like this, or expand some x plus y to the 5th power, something like this. Instead of multiplying and multiplying and multiplying, you can just use the coefficients here, and this expansion is very beautiful. And here, a first example using the binomial theorem really comes from, it's really calculation. We want to find the coefficient of x squared, y to the 5th in this. Okay, well, binomial theorem says this is a sum. K would go from 0 to 7 of 7 choose k. We would have 2x to the k, y to the 7 minus k. Now, if you just match up, right, what do we want? We want the coefficient in front of x squared, y to the 5th. And you see this involves using k equals 2, this term. So the k equals 2 term looks like this. It would be 7 choose 2. It would be 2x squared and then y to the 5th power, which is 7 choose 2, 2 squared, which is 4, and then x squared, then y to the 5th. And now we see what the coefficient is. It is 4 times 7 choose 2. So the answer is 4 times 7 choose 2. And I will leave it like this for now because we don't have a general formula yet for these binomial coefficients. So I'm going to leave my answer with the binomial coefficient in it. Okay? Now, let's do a proof with the binomial theorem, except what I want you to remember from this board is this 1, 3, 3, 1, because this will come up very soon. So let us use the binomial theorem in a proof. Let's use the binomial theorem to prove this identity. And this is what's called a combinatorial identity. We will prove this exact same one in the very next lesson using something called a combinatorial proof, which is also quite beautiful. But for today, we are proving it this way. Use the binomial theorem. Okay, here we go. Let's let x equal y equal 1 in the binomial theorem. Then, what does the binomial theorem say? Well, 1 plus 1 to the n will be, it says it's a sum, k equals 0 to n of n choose k, 1 to the k times 1 to the n minus k. This is exactly the binomial theorem. Now, 1 plus 1 to the n, this is 2 to the n. So I'll say rewriting, we get 2 to the n, and 1 to any power is 1. So this is n choose k times 1. And this is the end of our proof using the binomial theorem. Frequently, and you will see me do this throughout the semester, you can put a box to denote the end of your proof. Recall, I told you to remember this 1, 3, 3, 1 that was on the board. These were the binomial coefficients, 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Well, now I will introduce something called the Pascals Triangle. This is an infinite triangle and is one of the most beautiful things in math. Well, how do we make this? The border consists of all ones. And then any interior value is the sum of the two numbers above it. And this creates this infinite Pascal's triangle. So let me do some number of rows. Now we have ones on the border. Let's fill in some interior values. This would be here, 1 plus 1. This is 2. This would be 3 and 3. Okay, we already see this 1, 3, 3, 1. But let's continue. Here we would have 4, and here we would have 6 and 4. And now we move to the next line. 5, 10, 10, and 5. And now the next line, we would have 6, 15, 20, 15, and 6. Okay, and then maybe I'll have room for one more. Put the 1, and then this would be 7. This would be 21. This would be 35. Another 35. 21, 7, and 1. Okay, and this is as much as I can fit. This is Pascal's triangle. Okay, it continues forever. And now I mentioned we see this 1, 3, 3, 1. Well, let me just change. So there's going to be some special effects here. Okay, I'm going to change. The beauty is I am still looking at Pascal's triangle, okay? You see here, the border is all ones because we have discussed that any non-negative integer, choose 0 is 1, and then n, choose n is also 1. And then we have this 1, 3, 3, 1 appearing here, and this is what we see, okay? So this is Pascal's triangle. It consists of the binomial coefficients arranged along rows. Now, what is it that makes this hold? Right? I told you how to create Pascal's triangle, which was any interior value is the sum of the two numbers above. Well, here is an interior value that I took as the sum of two numbers above. So what this says, okay, let's translate it for general, or we could take another interior place. But the identity here is as follows. It says if you take n, let's say choose k minus 1 plus n choose k, that this equals, here's n choose k minus 1, n choose k, is equal to, you see it, n plus 1 choose k. This is an identity. In fact, it's called Pascal's identity. It's what really makes this with the purple the same thing that we saw with the blue. The triangle is using borders all ones and this Pascal's identity. And we will prove Pascal's identity next time. It will be a combinatorial proof that we do in our very next lesson. We will end today by getting a formula for the binomial coefficient n choose k. The way I will do this is I will count k permutations of n elements in a different way than we have thought about them before. And then sort of use that we know p and k counts these. It will give us a formula, as we will see, for n choose k. But I want to make this comment before I start counting these. And what is p and n? Well, we know what this is. Looking at the formula, it would be n factorial over 0 factorial. And 0 factorial is just 1. So this is n factorial. This is counting, well, if you interpret it this way, it would be just all permutations of n elements. So this would be all orderings of n elements. That's in this framework, but we could have thought about this without this p and n notation. Just think about n factorial. Okay, how am I going to make an ordering of n elements? Let's say n is 5. I want to use all 5 and line them up. I have 5 options to put here. And then in the second spot, now I have 4 options because I can use any of the 5 except the one I've already used. And then I have 3, and then I have 2, and then I have 1. Multiplication rule, we would have 5 factorial. So this is another way to think about n factorial. This quantity is the number of ways to permute n items, sort of in a line. Okay, now back to the task at hand, which is we want a formula for n choose k. So let me maybe just erase this. How I will do this, as I mentioned, let's count k permutations. We will make a k permutation of n elements in 2 steps. Step 1. Well, we have n elements, and we can just select k of them that we want to use in our permutation. And step 2, let's order the k elements. This will give us a k permutation. Now let's just count. Well, in step 1, how many ways to do this are there? There are n choose k. We're just selecting the k elements. And in step 2, order them. Now we have k elements, and we want to order them. And this goes back to this discussion, except it's k factorial. We have k elements in our hand unordered, and we want to order them. K factorial ways of doing this. So altogether, multiplication rule. we have n choose k times k factorial, k permutations. And that must equal this. It must, because they are both counting the same thing. And this is really, well, the whole idea we will use next time with our combinatorial proof. But this counts k permutations of n elements, and this, through this two-step process, also counts the k permutations of n elements. So that means they're equal. We get n choose k is n factorial over k factorial times n minus k factorial. This is exactly the number of k element subsets of an n element set, n choose k.